Yesterday we have started heat part. In that, the thermal properties of matter is completed. Now the remaining synopsis I will complete first, and afterwards we'll complete these numericals. Then we go to the other chapter. Most probably within 3 or 4 classes, I should complete this first PUC part, and I will go for second PUC part, because more weightage is there for the second PUC, right? Then let us suppose a body that falls from a height h. If a body of mass m falls from a height h onto the ground, then what happens? It will gets the heat. If it falls from height h and reaching the earth, it will get the heat. So then work done is proportional to heat produced. Work done is equal to heat produced. Then work done W is equal to J into H, where J is called as the proportionality constant, called Joules constant. The value of J is 4.186 joule per calorie. 4.186 joule per calorie. J is a constant. This is not joule. J is a Joules constant. It is constant. 4.186 joule per calorie. Otherwise, J is equal to 4.2 joule per calorie. We write joule per calorie. We may write. So 4.186 joule per calorie or 4.2 joule per calorie. We write. Right. If the body that falls from height h onto the ground, then what happens here? Potential energy will be there that will convert into heat energy, that will produce that heat energy. Then potential energy PE will be converted into heat energy. PE is equal to J into Q. PE is equal to J into Q. There. Potential energy PE is equal to mgh. mgh is equal to J into. So as it gets the heat, Q is equal to ms into theta. Q is equal to ms into theta. Both sides will get cancel mass. Then what is there? Specific heat S is there. So S is equal to GH divided by J theta. Specific heat S is equal to GH divided by J theta. This is the expression for the specific heat. Specific heat not. We have to calculate how much heat it will get, how much the temperature it will gain. We have to take. So theta is equal to GH divided by theta is equal to GH divided by J into S. Theta is equal to GH divided by J into S. This is like if it falls from height h1 and rebounds to a height h2 in such case. It falls from a height h1 and rebounds to a height h2. It falls from height h1 and rebounds to height h2. Then heat gained, the amount of the heat gained by it is we have to take. Then mg into it falls from height h1 and rebounds to height h2. h1 minus h2 is equal to J into ms delta theta, or simply theta. So then both sides mass will get cancelled. Mass will get cancelled. Then d theta is equal to G into H1 minus H2, G into H1 minus H2 divided by J into S. This is that. Let us suppose, a bullet is a fight. A bullet is a fight, and it against a target. Then on firing the bullet, if it is embedded in it, and it will get the heat. When a bullet is a fight, it penetrates to the target, and it gets the total of the heat will be utilized to one is to produce the heat, and other one is to certain amount of the heat will be utilized to melt it. In that case, we can take. So what is that? When a bullet is a fight, it moves with some kinetic energy K. Whenever it hits the target, on hitting the target, what happens? It will absorb the heat. So only if it absorbs the heat without melting, then we have to take like this. Then kinetic energy Ke is equal to half mv square, and that heat absorbed will be equal to Q is equal to ms into delta theta. From this we will write that half mv square is equal to J into ms into delta theta. Both sides mass we will get cancelled. Mass gets cancelled. Then how much temperature difference that is caused, that we have to take. Delta theta is equal to V square divided by 2JS. So what is this? A bullet is a fight against the fixed target, against a target. Then its kinetic energy will be utilized to provide that specific heat. Means what? Increasing of temperature. Here only absorbing of the heat is there. Instead of this absorbing of the heat, if bullet also melts, then in such case, in this case, by along with the absorbing heat, bullet also melts. In such case, half mv square, it is a kinetic energy. So this kinetic energy utilized to provide, one is by absorbing it, other one is by to melt it. ms delta theta plus m into L, that we will take. So this is that specific heat. This is called as latent heat. If the temperature of the bullet that increases, we'll take that specific heat. If the bullet melts, in that case, we'll take the latent heat in terms of the latent heat. Like this, we will take. Next, isothermal process. The process in which temperature is constant, pressure of the given mass of the gas is inversely proportional to volume. This is called isothermal process. Pressure is taken along the y-axis and volume is taken along the x-axis. This graph is called as the PV diagram or indicator diagram, we'll say that. Then pressure P is inversely proportional to V, isothermal process. Next, area work done, all we'll write it. So expression for that isothermal process is PV is equal to constant. Isothermal process is a slow process, melting of ice, vaporization of the water. Work done for this RT log V2 by V1 base E. This is the work done in isothermal process. Next, adiabatic process. Adiabatic process. The process in which temperature, pressure, volume, all they change is called as the adiabatic process. The process in which temperature, pressure, and volume, all of them they'll change, is called as the adiabatic process. The process in which pressure, volume, and temperature they'll change is called as the adiabatic process. In that adiabatic process, PV is equal to constant. PV is taken as a constant. PV is equal to constant that we will take. For adiabatic process, PV is taken as a constant. Otherwise, we may write in other terms. PV is equal to constant, and TV power gamma minus 1. TV power gamma minus 1 is also taken as constant. One more expression. Then pressure and temperature, both we have to take that. So in terms of the temperature and pressure, T power gamma, P power 1 minus gamma is taken as constant. These are the expressions. And the work done in adiabatic process. Work done in adiabatic process are divided by gamma minus 1 into T1 minus T2. This is the work done in adiabatic process. Right? Next, isobaric process. The process in which pressure is constant is called as that isobaric process. The process in which pressure is constant is called as the isobaric process. Next, isochoric process. The process in which volume is constant is called as the isochoric process. The process in which volume is constant is called as the isochoric process. When we plot the graphs, PV diagram or indicator diagram will say that. So PV diagram or indicator diagram, we will when we draw for this PV diagram or indicator diagram, whenever we draw, this is pressure is taken along the y-axis, and PV diagram, volume is taken along the x-axis. This is isobaric process. This is isochoric process. What is this? Isobaric. Pressure is constant. This is isochoric. Isochoric process. This is isothermal. Isothermal process. And if I take it's like this, it is the adiabatic process. Adiabatic. This is. Or if I take the graph opposite to this. Pressure is taken along the y-axis, and volume is taken along the x-axis. If I take this as a point, this is a isobaric process. This is isochoric process. Isochoric process. This is adiabatic process. Isobaric. Isochoric. This is called adiabatic, isothermalities, isothermal processes. So the work done when we take that, work done in the clockwise is taken as positive. Work done in the anti-clockwise is taken as negative. Let us suppose a body, this is a PV diagram or indicator diagram. In the PV diagram, if the body that moves from the point A to B, if it moved from the point A to B, from A to B, it has moved. Then the area covered by this will give the work done. So this will be that work done. Work done is equal to pressure difference into volume. Work done is equal to pressure into difference in volume. Work done W is equal to P into V2 minus V1. This is the work done. So work done in the clockwise is taken as a positive. Work done in the anti-clockwise is taken as negative. Let us suppose this is like this. These are the PV diagrams or indicator diagrams. PV diagram. This is the PV diagram. This is a anti-clockwise. The work done is taken as positive for the clockwise and negative for the anti-clockwise. Like this, we will take. Next. These are the graphs. And so then when we come to that Carnot cycle, Carnot engine. Efficiency of the heat engine. Let us suppose this is that source which is maintained at very high temperature. Source. It is maintained at a low temperature called as the sink. Then so heat will drawn from this. Out of it, Q2 is given to the sink. The remaining will be utilized to do the work. Q1 minus Q2. The efficiency of the engine when we take efficiency, eta is equal to work done by heat drawn. So efficiency of the heat engine, eta is equal to Q1 minus Q2 divided by Q1. This is called efficiency. And for the refrigerator, whenever we take that refrigerator, we'll say that beta is that beta is equal to Q2 divided by W. So therefore, beta is equal to Q2 divided by Q1 minus Q2. This is the efficiency of the Carnot cycle or Carnot engine. Fine. We'll solve the how many problems are completed yesterday. We'll check this. We didn't start the problems, I think. Okay, we'll see that. First law of thermodynamics that gives that when the heat is applied to a substance, certain amount of the heat will be utilized to increase its temperature, and remaining amount of the heat will be utilized to do some external work done. So some amount of the heat will be utilized to increase its internal energy. When dq amount of the heat is applied to that, out of it du is to increase the internal energy, and dw is to do some external work done. So dq is equal to du plus dw. du plus dw. So therefore dq is equal to du plus dw means what? pdv also we correct. So whenever we supply the some amount of the heat to that substance, one part of heat is to increase the internal energy, and the remaining part is to do some external work done. This external work done is nothing but in increasing the gas. So du is that increase the internal energy. Increasing of internal energy is nothing but increasing of temperature. If temperature increases, internal energy of the gas also increases. See, according to the first law of thermodynamics, so dq is equal to du plus pdv. For the small changes in the volume, pressure will be taken as constant. So dw will be written as dw is equal to pdv, we will write. dw is equal to pdv. So what is that? So dq is the supplied heat. Out of it, one part of it is to increase the internal energy. Other part is to do some external work done. Then the internal energy of an ideal gas depends upon the temperature. Internal energy of the gas depends upon the temperature. Next, in changing the state of thermodynamics, from point A to B state, the heat required is Q and the work done by the system is W. The change in internal energy is. So if you want the change in internal energy, the same expression we may take that. What is that? Heat supplied is taken as a dq. That is taken as a Q. Q is the heat supplied. Out of it, one part of it is increased internal energy, other one is to do some external work done. Okay, from that internal energy U is equal to Q minus W, we will write Q minus W. Right, next problem. Heat given to 35 joules. Heat given to 35 joules. And the work done by the system is 15 joules. The change in internal energy. So the change in internal energy directly we may write. What is that formula? dq is equal to du plus dw. Then we'll write du is equal to dq minus dw. dq is equal to du is equal to dq minus dw. So then what is given data? Heat given to the system. dq is given as 35 joules. And the work done by the system is given as dw is equal to 15 joules. 15 joules. Then change in internal energy of the system will be change in internal energy dq is to be calculated. du is to be calculated. So du is equal to dq is how much? 35 minus dw is equal to 15. Therefore, du is equal to 35 minus 15, it will be equal to 20. 20 joules is the answer for it. Right? Next, the temperature of an ideal gas is kept constant as it expands. the gas does external work. During this process, internal energy of the gas is the temperature of an ideal gas is kept constant. What did they say? The temperature of an ideal gas is kept constant and it expands. And as it expands, the gas does external work. During this process, the internal energy we have to take that. So internal energy that depends upon the temperature. So as the temperature of the gas is kept constant, the internal energy remains same. As the internal energy depends internal energy depends only on temperature. As temperature is constant, internal energy constant. Internal energy also constant. Internal energy also constant. Internal energy remains same that we have to take. Internal energy remains the same. Next. First law of thermodynamics is concerned with the conservation of energy. First law of thermodynamics that is concerned with that energy. That's concerned with the energy. Next. And a thermometric system goes from the state P1, V1, P1, V2 to P1, V, then PV2, P2V. Then the work done in this case is, first case work done, first case, what is that? That is work done. In the first case, work done is to be calculated. Case 1 will take that. Case 1. In that case of thermodynamic system goes from the state P, V, P1, V2 to P1, V. So work done dW is equal to P into V1 minus V2. So whenever we take this, dW is equal to P into V1 is V, V2 also equal to V. V and V. These two gets cancelled. V and V get cancelled. Therefore, dW is equal to 0. First one. Second. Case 2. Then dW is equal to P into V1 minus V2. In the second case, P and V. V1 is taken as a V and V2 is taken as 2V. Therefore, we'll write dW is equal to P into V is taken as a V. V2 minus V1. As pressure, V2 minus V1 will take it. V2 minus V1. So V2 is taken as a V. This is taken as a V1. It is a V2. Therefore, in this case, dW is equal to P into V2 minus V1 will write. Here also V2 minus V1 make it. Then dW is equal to P into V2 minus V1. So dW is equal to P into V2 is taken as a 2V. V1 is taken as a V. Therefore, dW is equal to P into V. First one is 0. First case 0. Second case dW is equal to PV. 0 and PV. This is the B option is correct. 0 and PV. That one is there, one is not. P1 into V. Right. If the amount of the given to a system is 35 joules, amount of the heat is given to the system, dQ is equal to 35 joules. And amount of the work done by the system is dW is equal to minus 15 joules. Minus 15 joules. dW is equal to minus 15 joules. Then the change in internal energy of the system is, so dQ is equal to du plus dW. dQ is equal to du plus dW. Then du is equal to dQ minus dW. Then du is equal to, dQ is how much? 35 joules. Minus 15. This minus of minus 15. Minus of minus 15. Then du is equal to 35 minus of minus 15 plus. So du is equal to 50 joules. du is equal to 50 joules. A system given as 300 calories of the heat and it does. A system is given 300 calories of the heat and it does 600 joules of work. How much does the internal energy system changes in this process? So 300 calories of the heat they told. We need that in the joules. So that heat given, dQ is given as 300 calories. That we have to convert into joules. dQ is equal to 300 into 4.186. 300 into 4.186. On multiplying this, we will get it as 654, like 654. 300 into 4.186. If you take the 4.2, nearly 300 into 4.186. 4.18 will take it. Up to 4.18 if you take, this will be 1254. So dQ is equal 300 into 4.18 will be equal to 3 4s are 12. So 1254. Then dW is given as 600 joules. What is du? What is du? Then dQ is equal to du plus dW. dQ is equal to du plus dW. Then dQ is equal to du plus dW. Then du is to be calculated. du is equal to dQ minus dW. du is equal to, what is dQ? 1254. 1254. dW is given as 600. So therefore du is equal to 654 joules. 654 joules it is. Next, work done or by a gas in general depends upon work done or on or by a gas in general depends upon work done that depends upon initial state, final state, and path followed. But if it is internal energy, it depends only on the temperature. Internal energy is a unique process. It depends on the increase in temperature. Work done or by a gas in general depends upon initial state, final stage, and path followed. If R is the universal gas constant, amount of the heat needed to raise the temperature of 2 moles of an ideal monoatomic gas from 273 kelvins to 373 kelvins, no work is done. It is given that the amount of the heat needed to raise the temperature of 2 moles of an ideal gas, then heat needed to increase the temperature of amount of the heat needed to raise the temperature of 2 moles of that ideal gas. It is given that number of moles of the gas. If I take number of moles of the gas, F is equal to 3. So I have to say here, then monoatomic molecule. What is meant by monoatomic molecule? A molecule which consists of single atom is called as the monoatomic molecule. If the single atom molecule is moving along the x-axis, it requires only one variable. To study it, it requires only one variable. If it is moving along the y-axis, only one variable. It is moving along the z-axis, only one variable. Instead of that, if this monoatomic molecule that moves in the space in that x, y, z, it is. So if the monoatomic molecule is moving in the space, then number of independent variables to specify it along that x-axis, y-axis, and z-axis. X, y, and z. X, y, z. All these are needed to specify its position. With respect to x-axis, it is at certain distance. With respect to y-axis, it is certain distance. With respect to z-axis also, it is at certain distance. So it depends upon 3. These 3 independent variables are called as number of degrees of freedom. That we call number of degrees of freedom. So then for monoatomic molecule, number of degrees of freedom, F is equal to 3. For monoatomic molecule, F is equal to 3. For diatomic molecule, number of degrees of freedom is taken as 5. And for polyatomic molecule, number of degrees of freedom, F is equal to 6. For polyatomic molecule, F is equal to 6. These are the then specific heat ratio gamma. Gamma is that ratio of the Cp by Cv. Or we'll take that Cp by Cv, Cp minus Cv is equal to Cv. Cp is always greater than Cv. Cp minus Cv is equal to universal gas constant R. Cp minus Cv is equal to universal gas constant R. And we may take that Cv is equal to R divided by gamma minus 1, and Cp is equal to gamma R divided by gamma minus 1. These are the expressions for the specific heats in terms of this. And when we take that specific heat ratio for the monoatomic gas, diatomic gas, polyatomic gas, if you take that, polyatomic gas is nothing but triatomic gas. Then specific heat ratio, gamma is equal to 1 plus 2 divided by F in terms of number of degrees of freedom. For monoatomic molecule, this gamma is equal to 1 plus 2 divided by this F is equal to 3 for monoatomic molecule. Therefore, gamma is equal to 3 plus 2, 5 by 3 means what? 1.66 like that. This is for monoatomic. And for diatomic, gamma is equal to 1 plus 2 divided by f. Gamma is equal to 1 plus 2 divided by. So number of degrees of freedom is taken as 5. Gamma is equal to 7 divided by 5. Gamma is equal to 7 divided by 5. Next, for triatomic. For triatomic molecule, number of degrees of freedom is taken as 6. Gamma is equal to 1 plus 2 divided by 6. Gamma is equal to 8 by 6. That will be equal to 4 by 3. 1.33. This is the specific ratio. In this problem, what did they give? How much heat should be supplied to increase that amount of the heat is needed to raise the temperature of 2 mole of the ideal gas. Number of moles of the gas is given as mu for number of moles of the gas 2. And monoatomic, they told it. Monoatomic number of degrees of freedom, small f we take. Small f is equal to 3 for monoatomic. And ideal gas from 273 kelvins to 73 kelvins. Then temperature difference, delta theta is given as 270 to 373 means what? 100 degrees centigrade, 100 kelvins. Then how much amount the heat is needed? How much amount of the heat is needed? dq is equal to 1 by 2 mu f r into delta theta. This delta q is dq is equal to 1 by 2 into mu means number of moles of the gas 2, number of degrees of freedom is taken as 3, r into delta theta is taken as 100. 2 and 2 get cancelled. 3 into 100 it will be t100. So dq is equal to 300 r. dq is equal to 300 r. dq is equal to 300 r. Find the change in internal energy of the system when system observes 2 kilocalories of the heat, and the same time it does 500 calories of the work. 500 calories of the work it will do. 2 kilocalories, and at the same time it does 500 calories of the work. Find the change in internal energy of when system observes 2 calories. dq is given. dq is given as a 2 kilocalories. 2 kilocalories means dq is equal to 2000 calories. 2000 into 4.2 joules. From this we will write dq is equal to what? dq is equal to 2000 into 4.2. 2000, it's 8400. Then what is that? And the same time 500 joule of work is done. Work done will be how much? dW is equal to 500 joules. Work done is equal to 500 joules. Therefore du is equal to dq minus dW. From there du is equal to dq is how much? 8400. 8400 minus 500. Therefore du is equal to 7900 joules. 7900 joules. Next, 110 joules of the heat. 110 joules of the heat is added to a gaseous system whose internal energy changes is 40 joules. Then the amount of the external work done is. What is given? 110 kilojoules of heat is added. dq is equal to 110 joules. Added system whose internal energy is du is equal to 40 joules. 40 joules. Then the amount of the external work done, dW is equal to amount of external work done. dW is equal to dq is equal to du plus dW. Then the amount of external work done, dq is equal to du plus dW. Therefore, dW is equal to dq. dW is equal to dq minus du. So dW is equal to dq is how much? dq is 110 minus 40. Therefore, dW is equal to 10 to 170 joules. Taken as 70 joules. Which of the following is not the thermodynamic function? Which of the following is not the thermodynamic function? Work done is not the thermodynamic function. Enthalpy, internal energy, Geber energy, all these are. Work done is not thermodynamic function. Work done is not the thermodynamic function. Next. When the amount of the work is done is the 3,300 joules. Sorry, the amount of the work done is 333 calories, and the change in internal energy is 167 calories. Then the supplied heat is, all of them they have given calories. That's why no need to convert into joules. Then the amount of the heat work done is dW is given as amount of work done. dW is given as 333 calorie. Then change in internal energy, du is equal to 167 calories. Then the heat supplied is dq is how much they have asked. Simply we have to add dq is equal to du plus dw. Therefore, we'll write dq is equal to du is how much? 167 plus dq 333. Therefore, dq is equal to 167 333. 333 167.
500.
500. It is 500 joules.
Calories, sir. 500 calories.
Sorry. Okay, actually, more weightage is there for the second PUC. It is better to stop that first PUC part here and we go for the second PUC because 40% and 40 bits, nearly 40 bits from the second PUC, 20 bits from the first PUC. So certain portion I have completed. Still, what is there? Waves, oscillations, so system of particles, and units and dimensions. That's a part is there. So after completing that second PUC, we will come to the first PUC. Then in next class, I am going to start the second PUC. First law of thermodynamics states that when the heat is supplied to the system, one part of it is utilized to increase the internal energy, other part is to expand the gas. Means nothing but to do some external work done. System can do work, system has temperature, heat forms. First law of thermodynamics states that system cannot do work. First law of thermodynamics states that system cannot do work, system has temperature, system has pressure, and heat is a form of energy. First law demonstrates that its system can do work. Yes, system can do work, we get right. System has temperature, system has pressure, heat is a form of energy. It is a form of energy. It gives that it gives the concept of energy. Yes. First law of thermodynamics, zeroth law that gives that that gives the concept of the temperature, and first law that gives the concept of the energy. First law of thermodynamics that gives the concept of energy. So this is a heat is in the form of this. We have to take it. It gives that concept of energy. Next. So thermodynamic process, 200 joules of the heat is given to the gas, and 1200 joules of the work is also done on it. The change in internal energy. Do this one.
Sir, 100 joule.
100 joules. The change in internal energy. That okay. Thermodynamics. 100 joules. It's completed. Okay. Actually, still little time is there. Even I am stopping here because I am going to start that next second PUC part. Within 3 minutes or 4 minutes, we cannot start the chapter. So then Monday, I am going to start that second PUC, which you feel difficult. That I'll start. You may say which you feel difficult. More weightage chapters are current, electricity, magnetism, moving charges and magnetism, dual nature of matter, semiconductors, nuclei, ray optics. These are the more weightage chapters. So if you suggest what you feel difficult, that one I'll start and I'll explain.
Sir, current electricity.
Dual nature.
Dual nature.
Optics.
Okay, this I'll take the priority. Dual nature, current, electricity, dual nature, and ray optics. I will take like this, but for dual nature there is no connection with that. But the current, electricity, little we require. So first I'll start the current, electricity. Next dual nature of matter. That next modern physics. Then I'll come for ray optics. Right.
Thank you, sir.
Thank you, sir.